Welcome to The Explainer. Today, we're diving into a secret mathematical rulebook, one that's hiding behind everything from your favorite 3D video games to the mind-bending world of quantum physics.
So what do quantum physics, 3D graphics, and even electrical engineering all have in common? I mean, they seem like they're from completely different universes, right? But it turns out they all share this one surprisingly elegant mathematical secret. It's a fundamental principle that, believe it or not, makes the super complex a whole lot simpler.
And the answer to that little mystery? It's a really powerful idea from linear algebra called the Cayley-Hamilton theorem. Now, just think of it like this. It's a secret instruction manual that's handed to every single square matrix.
This whole thing was first proven way back in 1853 by Arthur Cayley and William Rowan Hamilton. And what they discovered was pretty stunning. The theorem basically says that every matrix has its own personal rulebook, a very specific equation that dictates exactly how it's going to behave.
Okay, so if we're going to get a little technical for a second, the theorem says that every square matrix satisfies its own characteristic equation. I know, that sounds like a bunch of abstract math jargon, but just imagine it like this. That characteristic equation is like a unique algebraic ID card for a matrix. And the really cool part is that the matrix itself perfectly, and I mean perfectly, follows the formula written on its own ID card.
So let's put that in simple terms. In a nutshell, every square matrix follows the rules of its own characteristic equation. It's got this personal rulebook, right? And that rulebook is written in the language of a special polynomial equation. You know, those algebraic formulas with x's and exponents you probably remember from school? The theorem's big promise, its guarantee, is that the matrix will always follow the rules in its own book. No exceptions.
Okay, so we're talking about a matrix following a rule or satisfying an equation. But what does that even mean? I mean, how can a grid of numbers actually solve an algebraic problem? Let's break it down.
It's actually a pretty simple three-step idea. First, you find that special rule, the characteristic equation for your matrix. Step 2, and this is where it gets a little weird, you substitute the matrix itself back into the equation. So you literally replace the variable, let's say x, with the whole matrix A. And then, for the big finale, step 3. You do the math, and the whole thing just elegantly resolves to the zero matrix. It's like a self-fulfilling prophecy written in algebra. It always works.
All right, so a matrix follows its own rules. That's a neat mathematical trick, for sure. But so what? Why is this abstract idea so unbelievably important in the real world?
Well, because this theorem is basically a master key for simplification. Think about it. In all these complex fields, electrical engineering, quantum mechanics, 3D graphics, it lets us stop juggling these huge, bulky matrices, these big grids of numbers, and instead we get to work with a much cleaner, much more manageable polynomial equation. That's the secret. It's how a 3D graphics engine can rotate a character on screen so smoothly, or how an automated control system can process commands without getting totally bogged down in messy calculations.
But wait, because this is where the plot thickens. It turns out that characteristic equation, it isn't the only rule a matrix might follow. You can think of it as the official rule, sure, but it's not always the simplest one. In fact, a matrix can satisfy a whole bunch of different polynomial equations, not just its special characteristic one. These are called annihilating polynomials, which is a pretty cool name, right? They're called that because they all reduce the matrix down to zero. So what this really means is that a single matrix can actually follow an infinite number of different rulebooks. And that, of course, leads to a really fascinating question. If a matrix can follow all these different rules, is there an absolute simplest rule it follows? Is there a minimal rulebook? You know, the one with the lowest possible degree that the matrix still obeys? The answer is a huge yes. It's called the minimal polynomial. Here's the difference. The characteristic polynomial, the official one, for an n by n matrix, always has a degree of n. But the minimal polynomial, this new guy, can have a degree that's less than or equal to n. So, by definition, it's the most efficient, the most bare-bones, concise rulebook a matrix has. And here's the really beautiful part. The minimal polynomial divides every single other annihilating polynomial, and that includes the characteristic polynomial. This minimal rule is so fundamental, it's like the DNA of the matrix. It's a building block for all the other, more complex rules. It is the true core identity of that matrix. So when you step back and think about it, this abstract idea from the 1850s is still a key piece of the invisible software running the world around us. It's a perfect example of how pure math simplifies incredible complexity and reveals a deeper structure to things. Which just leaves you wondering, right? How many other hidden mathematical rules like this are out there, quietly running our world, just waiting for us to find them?